Suppose you're standing inside an elevator, and this elevator begins to accelerate upwards. You suddenly have the sensation where you begin to feel a bit heavier. Similarly, if you are in an elevator and the elevator begins to descend downwards, at that moment you begin to feel a little bit lighter. Are you really getting heavier or lighter? Well, that's nothing more than a mental deception of what's going on, and that's what apparent weight is all about. Now, before we move on, let's just deal with our rest condition. All right. So when the object is not accelerating, why do you feel weight in the first place? It has to do with the fact that the floor is pushing upwards against you. And the force the floor always acts against you is always known as the normal force. All right. And you're being pulled downwards due to the force of gravity. So if you were to draw this as a proper free body diagram, it would look something more like this. Okay, so our initial conditions when we take it the acceleration is at 0. First, let's create our Fnet equation. Fnet y is equal to, if upwards is positive, Fn, and logically, downwards would be Fg. All right, and when acceleration is at 0, well, we know that Fnet is equal to mass times acceleration. So if acceleration goes to 0, then the Fnet also goes to 0. So this term goes to 0. What this tells us is that the normal force will be equal to the force of gravity. In other words, the perception of what we feel like when the elevator is stationary is simply equal to m times g. So we have a control mass of 1 kilogram multiplied by the gravitational field strength here on Earth of roughly 9.81 newtons per kilogram. Then we get a normal force of 9.8 newtons. All right, that'll be our reference value. One thing I want to mention as well before we move on is that this illusion of rest mass, if you want to call it that, not that's a proper term, happens in two cases. It's either when the object is stationary, or let's say that we're ascending on our way to the CN Tower. Now, at first, when the elevator begins to accelerate upwards, yes, we suddenly feel heavier. But while the elevator is continuing its journey up to the saucer, you'll notice that there's no change in your weight. All right, you feel exactly the same as if you were here standing on Earth, and that has to do with the fact that your velocity was constant. All right, and if velocity is constant, acceleration is at 0. All right, it isn't until you're at the very top when the elevator begins to decelerate that you suddenly feel a little bit lighter. HTER, there, a little bit lighter. Okay, so let's go through the math of what's happening here. And we'll start off with the condition of, let's say that you're at the top of the CN Tower and you begin to accelerate downwards. Okay, and we'll use this as our number. All right, so we're accelerating downwards at 4.81 meters per second squared. Okay, we'll start off by creating our free body diagram. Here it is. And again, the whole idea of apparent weight has to do with how we perceive the normal force acting on us at our feet. Okay, so we start off with our Fnet equation. Fnet is equal to all the upward forces, subtract all the downward forces, and what are we going to do? Oh, since we know that Fnet is equal to ma, we'll substitute that into the equation. Now we just want to factor out the normal force because that's how we perceive our weight. So if we take our mg and we bring it to the other side, it'll become a positive term, and that will tell us that Fn is equal to ma plus mg. Okay, from here we can just sub in all our calculations. I know it's tempting to assume g is at negative 9.81 meters per second squared, but that's not the answer. Keeping in mind that you've already dealt with the minus sign all the way up here. All right, you've already mentioned to the reader that downwards is negative. So if you end up doubling your negatives over here, then it's going to throw off your calculations. Okay, I mean the real story is that when you're doing these calculations and you're creating your Fnet equation, it's really based upon a vector calculation, where the net of all your values is equal to the sum of all the individual forces. Okay, but when we treat it as a scalar, we're just telling us that the second value has a negative quantity, and we've already factored that in there. All right, so let's just sub in all the values, crunch them through, and again, as you accelerate downwards, you suddenly feel a little bit lighter. Remember our control value of Fn is equal to 9.8 newtons. All right, so that's how much a 1 kilogram object will feel if it's at rest. But as it accelerates downwards, it suddenly feels a little bit lighter. Okay, what about the other case? Let's say that we're at the bottom of the CN Tower and begin to accelerate upwards. And we'll just use this value over here. Okay, acceleration is at positive 3.0 meters per second squared. From experience, you might notice that you suddenly feel a little bit heavier, so your final answer should be greater than 9.81. Okay, so let's go through the calculations. For one thing, this a, at least in our head, will be flipped around the other way around because we're accelerating upwards. And our initial formula will look exactly the same. In fact, during all the rearranging, it will be the same formula. All right, so nothing has changed so far. The only thing that's different now is that we have a positive acceleration. So when we sub it into the equation over here, that will change our final result. How about you just pause the video right now and calculate it out? Hope that's enough time. All right, and you will get a normal force that will be greater than 9.8, around 13 at least in these calculations over here. One thing just to mention before we move on is that yes, these weights will change depending upon what's happening. So let me just draw the CN tower right here one more time. Okay, so if you're starting from the bottom and you begin to accelerate upwards, yes, you'll suddenly feel a bit heavier. All right, and as you decelerate to a stop, you'll suddenly feel a little bit lighter. All right, remember that deceleration is acceleration in the opposite direction. Okay, so that's why you'll suddenly feel a little bit lighter there. Similarly, if you start from the top of this CN tower and you begin to accelerate downwards, yes, you'll initially feel a little bit lighter. All right, but as you approach towards the ground, your acceleration is in the opposite direction now, right? Because as you're decelerating, you're accelerating upwards, and that's why at the bottom you'll feel a little bit heavier. Okay, so that has something to do with apparent weight, at least in one dimension. Now let's deal with apparent weight in 2 dimensions now, all right? Where you're going around in a circular orbit, like this car over here. Okay, from an earlier video, we covered that average acceleration would be when you connect these 2 vectors here from tail to tail. All right, because as you're doing average acceleration, you're finding out the difference in your velocity. And whenever you're finding out the difference, what you're really doing is you're taking 2 vectors, connecting them from tail to tail, and you're always comparing between the final answer. And that's why this is our delta v, that vector over there. And by definition, acceleration is equal to delta v over delta t. So we take our calculation over here and we divide it by the 1 second, and then we'll find out our average acceleration. I think this is all animated out. If you want to pause before continuing on to do the calculations yourself, by all means. I'm going to continue right here. All right. So we're effectively finding the hypotenuse right here. And the hypotenuse of these 2 that are squared with each other would be the square root of 2 squared plus 2 squared. All right. So the square root of 8, which would be, 2.828. Okay. Remember, you got to take that value, divide it by time, and you'll still get 2.8 meters per second squared. And you need to take a look at the original diagram to see the direction of your delta v, because your delta v over delta t will tell you the corresponding acceleration. Okay, so we're going to use this as our reference calculation, because this calculation here is not the correct answer for your instantaneous acceleration. All right, you're going to feel a different value in real life. What's happening in this problem over here is that your eyes are open right here. Okay, so you're observing the event over here. While you're going on the turn, your eyes are closed shut. You have no idea what's happening until you open up your eyes again at the end. So you have no idea whether if you went around a curve or you went around some crazy zigzag, or if you just simply took a shortcut. In fact, this calculation is based upon the assumption that's a shortcut. So you're traveling towards the east, you close your eyes. In fact, you're going at a diagonal, but you don't know any better. And then at the end, when you open your eyes again, you're traveling towards the south. And so this value over here will actually be lower than the actual correct answer. Okay? So how would we find out the real true answer? Well, we need to create a brand new equation for this. So let's go through how do we calculate out proper centripetal acceleration. Okay, it comes from calculus, and in fact, we're not going to talk about calculus over here, but we're going to deal with the simpler version of it, where we're going to assume that there's going to be these cute little pizza slices. All right, and these pizza slices will be our reference for these small little changes, which then we can take in a bigger assumption on average at the end. Okay, so we have a car that's traveling towards the east, and at some point in time, it's traveling at some diagonal. Okay, we don't know what it is, but what we do notice over here is that as long as we're traveling at a very small angle, the direction that we travel from point A to point B will be exactly the same as going around the circumference in the circle. Now I've exaggerated everything over here, so that's why you're going to see that these two lengths are not the same. But if I made it just a smidget in difference, less than a degree, you can arguably say that you're still traveling around the circumference of the circle. Okay, so I'm going to exaggerate it here just for visual reference, but you can imagine if we're just taking a very tiny pizza slice. Okay, so this slice that we've created over here, a few things just to keep in mind. R1 and R2 share the same value, so we're just going to simply call it R. And if you take a look at V1 and V2, at least as its magnitude, we're going to take it that the speed does not change as we go around in the circle. Okay, so they're maintaining the same exact speed. Okay, and that's why we call it uniform circular motion. Okay, so V1 and V2, we're going to simplify and just simply call it V as well. And in this pizza slice that we've created over here, do I have it animated out? Yes, I do have it animated out. We can create a relation here. And we'll show you the relation afterwards in the PowerPoint, because I'd like to show you another pizza slice that exists in this diagram here. And it's the one that occurs when you find out your delta V. Remember that your delta V is when you connect them together, at least a vector, from tail to tail. Your delta V is the vector that points from the head of V1 to the head of V2, like so. And for argument's sake, these two triangles are similar triangles. So in other words, whatever theta that you have going over here, it's the same exact theta going over here. All right, so if my turn was a lot more extreme over here, the theta here would be a lot more different, and when you connect the vectors from head to tail, yes, that angle will be much greater. Okay, again, we're not dealing with any extreme angles, we're just dealing with these very small, minute angles. All right, and we're going to compare the properties of these two triangles that we created, right? These two isosceles triangles. Okay, so for argument's sake, we can say that for the first diagram here, the relationship between the far end of this triangle and the radius, it's going to be the same ratio, right? So delta R over R1 is the same as delta R over R2, as you can see over here. And to make life simpler, we'll just say that it's delta R over R because the radius is the same in R1 and R2. We can make the same argument over here in the second triangle as well. So the relationship between the opposite end and one of the sides, it doesn't matter if you call it V1 or V2 because you're treating it as a scalar, that ratio will be the same. So as long as we assume that the thetas are the same, all right, their deltas are the same, and it's going to be a very, very small number, then we can make this argument that delta R over R is the same as a ratio of delta V over V. Okay, as they are both similar triangles. Something that hopefully you remember from back in grade 9. All right, next we're going to take our calculation of kinematics. All right, if distance is equal to speed times time, in this case over here, our distance is our delta R is equal to speed times time. Then we can sub that into equation number 1. Okay, so we're going to replace this delta R over here with V delta T, and it'll look something like this. Okay, one thing I want to point out is that there's a difference between V and delta V. Okay, V is a fixed number. Delta V is a difference between two separate numbers. All right, if you don't consider that, then unfortunately this formula here would never work out. Okay, A is not V over T. That's not true. Okay, acceleration is equal to delta V over delta T. All right, so you have to have a change in speed in order for you to have acceleration. If your speed is fixed, then there is no acceleration. Okay, so that delta does matter. You can't just erase it and pretend they're the same. So if these two are completely different, well, these two are the same. So what you can do is that, first off, let's just bring delta T down. Okay, so we're going to divide both sides by delta T just to bring it downstairs. Then we're going to take this V down here and bring it upstairs by multiplying both sides by V. And we end up getting something that looks like this. And if you recall, the definition of acceleration is delta V over delta T. Right, that's the definition of what acceleration is. So if that is true, then A is equal to V squared over R. There you go. That's the quick derivation of the centripetal acceleration formula. All right, and that's how it's derived. Yeah, this formula will be given to you on any quiz, test, or exam, but you'll need to know how to manipulate it and use it to solve for other cases as well. All right, so that's what we're going to talk about next. How to use this formula for other cases. No, in the following PowerPoint, sorry. This one we're going to do a mathematical example first, and then we'll take a look at that formula rearranged for other problems. Okay, So let's say that we have a very similar problem as before. So we're traveling at 2 meters per second, and I've already calculated out that the only way for you to go from here to here in that 1 second that we talked about, meaning that you have 4 cases of it, then your r has to be at 1.27 meters. Okay, you can go back to that previous example, example number 1, to calculate it for yourself. Okay, the radius has to be at 1.27 meters in order to get from here to here in 1 second, or to go full circle in 4 seconds. Okay. All right. So if we have our speed and we have the radius of turn, then what is the rate of centripetal acceleration? You can just, I guess, plug and chug over here, just sub in the value since you know what it is, and then it'll give you your centripetal acceleration value. And again, you can see that this value over here is higher than our previous one, because the previous one for average acceleration assumes that you've taken the path of least resistance, or the shortest cut. All right, so then your delta V would be a lot smaller than what it should be in real life. Okay, and I hope that you watched the previous video on average, what's it called, average velocity, because that was a video that which talked about why is it that your AC always points to the center. Okay, so please watch that video if you skipped ahead to this one, and I'll explain why is it that you're always accelerating to the center. And this was just a proof of the calculation. All right, it took 4 seconds for it to travel all the way around, just like in our previous case. All right, so even though we know the formula is AC is equal to V squared over R, sometimes we're not really given the speed. Okay, I guess not velocity, but the absolute value of velocity. Okay, so the speed is not explicitly stated. Well, we could also be given that, it took this many seconds for it to go around. Or if this event happens over and over and over again, the corresponding frequency. Okay, let's go through period first. Okay, by definition, for us to get around the full entire circle, that's equal to the circumference. The circumference to get around the entire circle. Okay, and that circumference corresponds to our delta D. Okay. And the time that it takes for us to go full circle, if it happens over and over and over again, then that will be known as our period, or capital T. All right. To find out the distance, or our circumference, it's equal to 2 pi r. So we can sub that in, and then we have this generic definition. Okay, so to find out the speed that it takes to get all the way around is equal to 2 pi r over delta T, or capital T for period. If we sub this equation into equation number 5, and just start cleaning it up a little bit. Again, we don't really call it delta T because this is happening over and over again, so we can drop the delta. Okay, and we end up with that. Okay, so that's another alternative way of calculating out centripetal acceleration. And the third way is what a period is not given to us, but the frequency is given to us. Do I have the shortcut method? I'm glad I have it here. Okay, we know that period and frequency are inversely correlated with each other. So what we can do is just a direct substitution into the formula. Okay, maybe I kind of skipped out on that. So AC is equal to 4 pi squared r all over, instead of t, we replace it 1 over f squared. Okay, and you can distribute the squared into each of the numerator and denominator inside the brackets. So it'll look like this. And whenever you divide a fraction by another fraction, the denominator of the second fraction becomes the new numerator, and that's why the final formula will look like this. Okay, so this is centripetal acceleration, including its 2 variant equations. I think that's it for today. So go through your homework, make sure you check your answers to your homework so that you can verify that you've done everything correctly, and I'll catch you in the next episode. Toodles!